Hi everyone, my name is Claire Tomlin and I'm a professor of electrical engineering and computer sciences at Berkeley. And this is the 8th in a series of modules that we're recording for the course EE221A, which is linear system theory at Berkeley. The topic of today's module is induced norms. We've introduced in the last module the concept of a norm, a map on a normed vector space which has certain properties. And we talked about vector norms, and we talked about some matrix norms. But by far the most popular matrix norms that we use are those that are induced from a linear operator, a matrix form of a linear operator. And we call those induced norms. So let's think back to our operator map function. We use those terms interchangeably, notation. And we'll use our notation A. Script A is a map from one vector space to another over the same field. So U over the field F to V over the field F. And we'll put some requirements on A. First of all, A is continuous. And it's a linear operator. Let's suppose that U and V are normed spaces. So associated to U, we have a norm, and we'll use our notation norm U. And associated to V, we have the norm V. So those are the norms on the spaces. Then we define the induced norm of the map A as the following. So I'm going to use I to indicate induced norm. That is equal to the supremum over all vectors U not equal to 0 of AU, and that's the norm taken in V, over norm U, and that's the norm taken in U. Okay, so it's an abstract definition. It's abstract because of, I think, a couple of things. First of all, we're looking at the norm of an operator, and we're thinking about measuring the size of the operator by how it operates on vectors in the individual spaces. So the second thing is that we include this supremum. So that means we're letting this vector U range all over the vector space U with the only stipulation that it not be the 0 vector. So this is meant to be the 0 vector in U. Okay, so it gives us some, as I said, some measure on the action of a linear operator. And so through this definition of an induced norm, we can now start to think about the application of this norm to the matrix representation of that operator. Or then more concretely, we could just think about the induced norm or different kinds of induced norms applied to matrices, where we could think of those matrices as being matrix representations of linear operators. There's a couple of things to say here about the right-hand side of this expression. The first is that this is said to be the norm in V, and this is the norm in U. So if we look at these vector spaces, typically in this course, we've been dealing with linear maps between vector spaces, where the vector spaces are finite dimensional vector spaces. U might be Rn, and V might be Rm, for example. And so when we think about this vector norm, we can use any vector norm in V that we like. Okay, so we've got a particular vector norm that we've chosen, but we all know that in Rn or Rm, there are a number of different vector norms that we have that we spoke about in the last module. And so we can then specialize these vector norms to be by our choice, and then thereby specifying the induced norm of the operator. So for example, we could then define the induced 1 norm. So I'm going to use the notation 1, I to mean the induced 1 norm, and that's simply this expression, the supremum over all U not equal to 0 of AU, and then this would be the 1 norm over norm U, and that would be the one norm. So that's assuming that we're using a space over which the one norm is defined. For example, in Rn, we have an expression for the vector norm, the one norm. And so similarly, if this were the two norm, we would define the right-hand side in terms of the vector two norm. Okay, so let's now go to some understanding now of what this induced norm, what concretely that induced norm is when we specialize to the one norm or the two norm or the infinity norm in the vector space. And that's really where we use this concept of the induced norm the most. Okay, so now we've got an operator A, which is taking R, or let's generally call it F over our field, Fn to Fm. And we've just written down, and we'll use the notation P to represent the particular norm we're choosing. So the induced P norm on the operator A is equal to the supremum over all vectors U, not equal to 0 of AU over U norm. Okay, and then in this case, this would be the P norm in the appropriate spaces. So if we look at, for example, the induced one norm is the supremum over all U not equal to 0 of AU over U, one norms. And we can show that that's equal to the following. It's the max over all J, and let J be our index in R or Fn. So J ranges from 1 up to n of the following set: the summation over the column index, I equals 1 to m, of the absolute value of Aij. Okay, so here, this notation here, it's the Aijth element of A, where we're thinking now about A, its matrix representation. So now we can think about the induced one norm on a matrix, and it's induced from this operator notation. So this is by definition. This equality needs to be shown. We need to be able to derive this quite concrete norm, which is a norm on a matrix, from this quite abstract definition of the operator A. If we look at what this is, we can see that we're taking the maximum over all indices j from 1 to n of this summation from I equals 1 to m. So if we think about what that operator is, that is the max column sum of the matrix. So it's something that's easily computable if you're given the matrix. The induced two norm of a matrix is, by definition, the supremum over all vectors u not equal to 0 of the two norm of AU over the two norm of U. And we can show that that's equal to the maximum over j from 1 to n, so the index j, of the jth eigenvalue of the matrix, which is A star A to the 1/2. Okay, so this product here, this means the conjugate transpose of A times A, so we have a matrix product. We note that A is not a square matrix in general, but A star A is a square matrix. So we're looking at the maximum, the square root of the maximum eigenvalue of the matrix A star A. And it turns out that the induced two norm, if you use this definition with these replaced by 2's, is equal to that maximum. So again, that requires proof. We haven't proven those. And then finally, for the other popular vector norm, which is the infinity norm, we can come up with an induced infinity norm on a matrix. And that's equal to the maximum from I equals 1 to m of the summation from j equals 1 to n of the absolute value of aij. And so it's the analog of this for the rows. So this is the max row sum. Again, given a matrix A, all of these entities are easily computable. And these are the typical matrix norms that we use. I think now what we should do is try to understand how we go from this induced norm definition to one of these very concrete forms. And so we're thinking about the induced norm on a matrix, and it's induced from the corresponding vector norm. So why don't we actually try to derive this relationship, to try to prove this equality, that this definition of the induced norm has this concrete representation. Okay, so we'll try to prove the first here. Okay, so proof of A. And for that, we need to remember our definition of the one norm for the corresponding vector space, Fn. And so we go back to our vector norms, and we remember that the one norm is simply, so if we had a vector x with elements x1 up to xn, then the one norm of x is simply the summation from I equals 1 to n of the absolute values x of the individual components xi. Okay, so that's all we need now to go ahead and take our expression for the induced one norm. So I have a matrix A, I'm computing the induced one norm. So by definition, that's the supremum. We'll use x here, it doesn't matter. So the supremum over all x not equal to 0 of ax one norm over x one norm. Okay, so this is a vector if we think about these spaces here. So this ax, that's matrix multiplication by a vector x. It's going to give us a vector in R or Fm. And this is just our regular x, a vector in Rn. And so I can now just apply, this is a vector. I can write out what the one norm is. I have the expression for it here. So that's the supremum over all x not equal to 0 of, and let's use the following notation. Let's just think about the ith element of that matrix product. So it's the summation from I equals 1 to m, there's m of them, of the absolute value of ax, and I'll use that to indicate the ith element of the vector ax. And we'll divide it, we'll write out the expression for x1. That's just the summation from I equals 1 to n of xi. Okay, and so now let's expand this. Remember, our goal is to come up with an expression. Well, we know the expression that we're trying to show. It's the max column sum. But that expression only depends on the elements of the matrix A, whereas still we have this supremum over all x not equal to the 0 vector of terms here which depend on x. So we're trying to perhaps isolate out the elements of A here, or figure out how we can isolate A. And so we'll further break down this expression. So this is the ith element of that matrix product. So I can rewrite that as the supremum. Let's write it back here. Going back here, that's the supremum over all x not equal to the 0 vector of the summation. And we'll keep that summation I equals 1 to m. And then the absolute value of the ith element of the product ax. So that's the summation from j equals 1 to n of aij xj. Absolute value, simply absolute value. over summation from I equals 1 to n of xi. Okay, and now I can start to perform some algebra on this. So I'm going to bring the absolute value inside the summation. I'm going to, and then I'll use an inequality here to bound that. So that's going to be less than or equal to the supremum over all x not equal to 0. And then I can just write this as the summation over I from 1 to m, summation over j from 1 to n of absolute value of aij xj. And you can start to see where this is going. So I'd like to somehow bring this out and simplify. So I can rearrange those terms. That's equal to the supremum over x not equal to 0 of, I'm going to reorder things a little bit. So bring the summation in j out. J equals 1 to n. Xj, absolute value, summation I equals 1 to m. And here I have the aij. And I'm missing here, no, that's good. Okay, so I've brought that outside the summation sign. And you should just check this to make sure that works. So these are finite summations, so we can do that rearranging. If you don't understand how we can do some of these manipulations, it's often good to just do a simple example. Take a 3x2 matrix, for example, and try these out just to make sure that you're clear about how these rearrangements go. But basically where we're going to get to, and I think I'm just going to leave the next couple of steps to you, is we'd like to be able to cancel out this term here, which is essentially the one norm of x, and end up here with just a term on the right-hand side, which depends on the absolute value of the elements of the matrix A. We're able to, so we're looking at all of the, we're ranging over all x in our domain such that those vectors x are not equal to 0, but we're trying to take the supremum of that expression. So choose the value of x which maximizes or supremizes that expression. So for example, we can show that this is less than or equal to, so I'm skipping a couple of steps here, the max over the index j of the summation from I equals 1 to m of aij. Okay, so I've done some cancellation there. And so I have almost what I need. I've taken out the supremum. I've replaced it with a maximum. So how did I do that? And also, I've got an expression which is almost what I want, that the induced one norm of the matrix is less than or equal to the maximum over the index j of this sum here. What I need to be able to show now is that in taking out that, in doing that supremum over x, there exists at least one x at which you can achieve that max value, at which you can achieve the supremum. And so here, I want to basically change that to equality by saying that the largest value that this expression can take on as I let x vary over all elements in the domain not equal to 0 is achieved for some x. And so we get, for example here, we would get equality, so I'm just going to say it's equal to the max if the x that I chose in the supremum is a vector which is all zeros except a 1 in the row where 1 picks out the max column sum. So this 1 here is placed so that when you perform this multiplication, you're pulling out the max column sum. Placed to pull out max column sum. So this is an illustration of the first case, the one norm or the induced one norm, how you can show that this quite abstract definition can be made into something quite concrete, which is this max column sum expression. So a nice exercise now to do would be to go through the second case for the two norm and the third case for the infinity norm and show that, similar to as we did here, when you instantiate those vector norms on the right-hand side with 2 or infinity, you get the expressions that we had, the largest eigenvalue of A star A, or the square root of that, and correspondingly the max row sum. Okay, so in today's module, what we've done is to study the concept of a popular matrix norm called the induced norm by starting with an abstract definition of the induced norm. And we think about the norm on the matrix A as being that norm which is induced by the matrix multiplication operation. So thinking about that norm as the corresponding vector norm when you apply A to vectors, when you think about A as an operator from one vector space to another. And moreover, we've shown that that abstract definition reduces to something very useful when we think about those vector norms in Rn as being either the one norm, the two norm, or the infinity norm. And we showed the process for deriving, at least for the one norm, how you would go from the abstract definition to the concrete representation. Typically when we use, I keep saying this, but typically when we use matrix norms, we're going to be using, we could use sort of general matrix norms that, like the Frobenius norm, for example. But really the most popular norms that we use for matrices are the two norm, so the induced two norm, the induced one norm, and the induced infinity norm. They're easy to calculate and they're easy to use. And so that concludes this lecture, this module on induced norms. Thanks.